This one works, I guess. Thanks, Ben. Thanks for the nice introduction. I can still see people are coming in. So it's a magnificent audience. And I just have about 30 minutes to talk about something which is really big of a topic, generative adversarial networks. So I really want to assure you that I belong to Henry VIII School of Public Speaking, in the sense that, as Henry VIII said to all his wives, I shall not keep you long. So now talking about generative adversarial networks, you can either call it GANs or GANs. I personally prefer to call it GANs because of the adversarial thing. You feel like shooting others, and that's quite nice in an academic environment as well. So moving forward, I will first start with the first word, generative. So what is really generative? So there are many ways of introducing it. I will rather introduce you in a contrastive sense. So what is discriminative? Discriminative is basically you have in a simple binary classification, two sets of examples, the reds and the greens, and what only you care about is the separating line, that black line. That's in its core what discriminative models are. And all the convolutional neural network success in classification problems, in object detection problems, these happen mainly towards discriminative. Generative, on the other hand, is something which is much more interesting and much more difficult at the same time. So if you really like to look at what generative is, so the idea here coming from the fact that generating realistic looking images is basically take you one step closer to understanding it. So in a very gross approximation, in a very jocular way, if you want to learn or understand what's the difference between generative and discriminative in medical imaging context, if you give your model input images and you get as output classification or regression just some numbers, then that's most likely discriminative. Whereas if you give it some images or not images but some random seeds and get as output some images, then you are talking about generative. That's a very jocular gross approximation, but that's probably a good way to start. Now, really, in terms of how generative adversarial networks are taking over the whole generative part, apart from the variational autoencoder, which we won't talk about today. So let's first look at some of the results that GAN can produce. They are quite interesting. So for example, if you see on the left, all right, it's somewhat, okay. So you can see on the left, we are talking about super resolution, and it's quite clear from the images that has been produced by the super resolution GAN that the really all the details are maintained in a much better way than compared to the other approaches. Whereas here it's more of the famous work by CycleGAN, and here you can show that you can do transfer of domains of images. So given images taken by your camera in your mobile, you can transfer them into the style of Monet, Van Gogh, or Cézanne, for example. And that's in the bottom is something which has been done in our lab. It was within a master's thesis, so it was more of a first try where we tried to predict the surgical video, the future frames of the surgical video based on the current frames using GANs. And as you can see here on the left, those are the real examples, and on the right, those are the reconstructions. Now, the second question there is, it's MICCAI, it's a medical imaging audience, so what's there in it for me? So I will just give you two examples of many, many excellent works that's being done on GANs. It's still coming up. And then one of the examples on the left is MR to CT reconstruction. So this is something you can think of as a problem where CT means you are putting the patient in lots of radiation. So what if you just have MRs and you try to reconstruct the CTs out of it? So that's one work that's been done in 2017. And it was quite interesting because day before, yesterday, we had a conference of radiologists in Frankfurt, and they already took notice of such an work. So from a radiology point of view, that's also quite interesting. On the right, you can see unsupervised anomaly detection from OCT images, and this is also done using GAN. So at this point, you are probably convinced that GANs are being present in medical imaging, but looking forward, what are the real medical imaging problems that can be solved by GANs? So I will give you 3 example cases where GAN as a technology, if comes out, might be able to provide you some solutions. One is basically proxy for training data. So you all know annotation is costly, and then there is data imbalance. The talk before talked about this particular problem. And if you can generate really realistic looking images from random fields, random sets, then you have a high hope that at some point those images can be used to train your discriminative network to solve certain problems, maybe diagnosis, maybe prognosis. The second thing is similarity metrics. So be it segmentation, be it registration, you have to develop some sort of similarity technique, be it dice score, be it some other form of scores, to really tell how good a particular method's performance is. And you try to get better over that metric. But these are hand-engineered metrics. When we are talking about deep neural network taking over the hand-engineered features, why not deep neural network takes over the hand-engineered metrics as well? And then there you have the possibility of using such adversarial training to solve the problem. And third example that I will show you is the case of domain shift, where domain adaptation is a big problem, and there you might have such GANs handy in solving the problem. All right. So at this point, let's look back at the actual thing and try to see what's really going on there, how we can make a generative model happening. So here you can see what was very traditionally a generative model. This is not something new. This has been there for some time, but the idea there is that you start with a random seed, Z, on the left, and then you have a generator of some form, a function approximator, maybe a deep neural network, maybe something else, that generates an image, which you call GZ. The idea of this is that if you want to make such a construct, you have to come up with a term, which is perplexity. Perplexity is the probability density function for the generated distribution. So in simple term, it basically means once you have your generator, given any image, it can tell you a probability that the generator has really outputted that model. So that's what perplexity is. Now the really interesting thing, the twist of GANs, is that it took perplexity out of the equation. And there are 3 main ideas that were used to take perplexity out of the system. I will tell you one after the other what these are. So sidestep the perplexity with deep nets, then use gradient feedback and game of many moves. So what each of these? So let's take a look at each one of the ideas and deconstruct them. So the first idea is sidestep perplexity with deep neural networks. So what does it mean? So you have this real world data distribution from which all the data are coming, of which you don't have much idea. But you now have a synthetic probability distribution from which you are trying to make as close to the real world as possible. So that's where the similarity kicks in. So now what you can really do, because deep neural networks are so good at discriminating, so why not we try to discriminate these generated images using deep neural networks? So what does it really mean? It means that these deep neural networks will take images as input and map them as between 0 and 1, based on how it thinks it's actually coming from the real data distribution. So that basically means you have 2 expectations. Expectation is really high when the data is coming from the real distribution, and the expectation is low if the data is coming from the synthetic distribution. That's what the discriminator's job is, to discriminate between data that's coming real versus the data that's coming from synthetic. All right? And as you all know, such a discriminator is pretty easy to train by now. You can just use simple backpropagation and this would work. So that's the first idea. Moving on, what's the next idea? The next idea is use that gradient feedback that you have got from your discriminator to actually also train the generator. So you not only train the discriminator from the gradient feedback, but you tell both generator and discriminator. So goal of the generator then is to basically make this expectation as high as possible, which in turn basically means you are trying to fool the discriminator into believing that the data that is generated from synthetic is as close to real. And if you can do that, then you can fool your discriminator. So basically here the backpropagation then is through this composed two networks. So you have D and you have G, and you are composing these two networks and doing a backpropagation through the composition of networks and trying to learn both discriminator and generator together. And this happens as a game of many moves. So at each point, generator tries to learn so that it can fool the discriminator, and the discriminator tries to figure out what is real, what is not real. So that's the real. So this is something which you normally take a look at when you talk about GANs. This is the general framework that's being introduced by Jan Goodfellow in 2014. And this is where you can see that the generator is basically only looking at the random seeds. It doesn't care about the real images, and from there it tries to generate images. And the discriminator is basically looking at both the real images and the synthetic images and try to figure out real and fake. And this is how the whole training is happening. Now, if you really turn it into a Minimax framework, this looks like this. So that's the game of many moves, basically. So you have this whole framework, but let's try to deconstruct. So as you can see here, there is a function f. So it can be more or less any increasing function, so that it makes sure that function of dx is high as possible. That's why you are trying to maximizing. Whereas this is trying to fool it, so you do 1 minus this, and then you are trying to minimizing it. So maximizing this means minimizing 1 minus this. This is together is what this whole formulation is about. Now, what really Jan Goodfellow did is his one big contribution apart from coming out the whole formulation is to figure out a function that does that. He chose fx equals log x, a simple log, because the derivative of log is 1 over x. What does it essentially translate is that the whole training is really, really sensitive to instances which d finds awful. So as long as you are doing okay-ish in synthetic, discriminator doesn't complain. But if you are really doing bad in generating synthetic images, then discriminator will create really high feedback that will make the generator to take really, really strong decision. And that makes the training into certain way so that overall the images look quite okay. So that's the general idea of GAN so far. Now, what really happened since this is that there is a whole industry of coming up with functions like that. That's the more theoretical industry of it. So coming out a new function with a nice behavior over the derivative and try to pull it in, see how it works. There are many papers like that, FGANs and stuffs. I have a slide where I introduce some of those. But what's really important is to look at the development of GANs, because GANs have really basically exploded rather than explored over the last few years. And if you look at the explosion of GANs, you can basically see there is a big divide between engineering explosion and the theory explosion. So when it comes to engineering explosion, you can fairly look into this recipe and take any paper, deconstruct it into its core form. So you basically look at input-output, you look at the architecture and loss function, and that's more or less any engineering GAN papers that's out there. Whereas if you are trying to look at the theory, it's more interesting because they are looking at the problem identification from a very numerics point of view, and there they have two different viewpoints. So either you go into the divergence viewpoint or you go into the game theoretic viewpoint, which I just now introduced. For today's talk, it's not really possible to go into the theory because we have 30 minutes to talk about. But what I will do is I will look into the engineering, and I will take two papers that are very common in GAN literature, and I will show how we can deconstruct this according to this recipe. So let's first look at DCGAN. That's deep convolutional GAN that has been introduced by Radford and his colleagues in 2016. It's a very, very highly cited, very famous architecture. And this is the first one where they really showed how nice the examples look like. So what really realistic example yet fake example generation means. And if you look at this thing, the input is basically Z. So you give random vector of whatever dimension, and then you get as output images. That's what it is. Now, if you look at the architecture, this is the architecture of the generator. So it basically takes as input 100-dimensional Z vector, and it gets as output 64 by 64 by 3 image. So 64 by 64 is the XY dimension, and 3 is the RGB color image. So you give as input a random seed, and from there you are doing deconvolution and generating images. And you have associated it with a discriminator that tells you how good or bad these images are, and you get better. That's what this paper is about. For the loss function, they still use the one more or less introduced by Jan Goodfellow. And this did pretty well. And since then, there are many more papers which talked about things like that, because this paper also had a sort of recipe which you can look at, and they told what sort of engineering tricks, so this leaky ReLU batch norm that you can use to make this network architecture more stable. I don't want to go into those details. But what I really want to show you is that there is another really famous framework, which is CycleGAN. And there the idea here is that you give as input an image, you get as output another image. And these are unpaired images that's coming from two different domains. So for a moment, let's try to think what it really means. So it really basically means that, let's say you are trying your network, your GAN, to take as input images that you have used your phone to take, and you are making images that look like Monet or Van Gogh. It's no way possible that you can have same images to train from. Van Gogh won't draw the paint the picture that you have taken with your phone. So you have a set of images that Van Gogh has chosen to draw, and you have another set of images that you have taken with your phone. These are two completely unpaired domains. And from there, you are trying to learn so that given these input images, you can generate such images. What's the medical equivalent? The medical equivalent is MR and CT pairs. So even for the same patient, if you consider, you won't get MR and CT which are pixel-wise registered. It's kind of impossible to do that. And if you now consider between patients, there are many, many variabilities. And how to take one such image as input and make it into another domain, that's the part of this CycleGAN architecture. In its core, the idea is quite simple, yet very, very interesting. So what they really do is the following. This is why it's called cycle, because it looks like one is going front, one is going back. The idea here is that you use two generators and two discriminators instead of one generator, one discriminator. So the two generators, what it does is like it takes, the first generator G takes images from domain X and generate domain Y, whereas generator F takes images from domain Y and generate back to X. And then for each of the domain of generation, you can put a discriminator that says for that particular domain whether it looks realistic or not. That's the overall framework. Now, if we bring it down, we deconstruct it, this looks basically like this. So you have your domain X, which G is taking as input and producing some images at domain Y, which you are looking into your discriminator and trying to figure out whether they look realistic or not. And you are doing the same thing for the other one. The loss function is where the second fun part comes in. So what you really are trying to do is that you don't have paired images. So you don't know where these images in domain X will land at domain Y. What you can ensure is that these images, when go through the second cycle, should end up at the same place. They might not. But the idea here is that then you can use that difference of where it started and where it ended as an extra loss function that tells you how good your training is. You do that for X domain, and you do the same thing for Y domain. And that creates your cycle consistency loss. And then if you look at the CycleGAN loss, you have basically two discriminator loss, the simple GAN losses for both of the discrimination, and then they have the third cycle consistency loss. And these together is creating your learning problem. All right? So now the second or the most interesting part for this audience is GANs for medical imaging applications. There are quite a lot of applications that's been going on. I introduced just briefly 2 of them, but there are many others. So what we really did is like we wrote a GAN review, which is already in archive, submitted there on Thursday, should be available by tomorrow if archive guys don't make any more problems, where we looked at 63 papers that were published till MICCAI 2018. And we are also giving you a first glimpse of how the distribution of papers are. So not surprisingly, the most explored application is synthesis. You can see almost 40% of the papers come there. But there is also, quite interestingly, that segmentation is taking the second big chunk of these papers. So what it really means is that you are looking at segmentation and probably looking at not just as a metric the dice coefficient for training, but you are using such adversarial losses as your training to get better at segmentation itself. And then, of course, there are reconstruction and other applications. That's so far all good. Probably are excited if I have done a good job. But let's look at some of the problems that's associated with GANs. So one of the first problem is numerical instability. So GANs are very, very unstable, and there is an associated problem which is quite common in literature, which is called mode collapse. So basically, many seed points are being collapsed at one particular image, and that means you are generating images that look similar rather than you are actually exploring the real distribution from which the images are coming from. However, there are some recent work that's going on to look at this mode collapse problem from a numerical perspective. And I will just briefly introduce you the first idea of what's really going on. So I will first give you an extreme example, which is constant curl vector. And that's a non-conservative vector field. What it really boils down to, this means if you do gradient descent in this vector field, you will keep on moving on circle again and again. Even though there is an equilibrium, a clear equilibrium exists there, you will never be able to reach there. Now GANs, by design, are zero-sum game. So how much discriminator does bad is what exactly generator does better. And for such a zero-sum game, this kind of simultaneous gradient descent ascent formulation generalizes into such non-conservative field. That's a very, very numerical result The problem that means that you will face more and more mode collapse unless you are taking real steps into making sure that this is not happening. That is numerical optimization steps. The second thing is that as evaluation metrics, what do you choose? It's all great that you can generate these very pretty pictures, but how do you evaluate how pretty these pictures are, how realistic these pictures are? You can do Amazon Mechanical Turk, you can take another deep neural network that was trained only on real images and then put them there, see whether they do classification. These are some of the things that people do. But is this everything? We have no really nice way of evaluating what GANs are doing. And I will show you some very practical things where GANs do wrong. First, counting. So GANs are not really good at counting unless you are specifically conditioning it to count. So in medical imaging equivalent term, that means if you are trying to generate cell images where you have many cells, it might end up doing weird things which are not realistic, yet your discriminator will tell you, yes, that looks exactly like realistic. That's the first problem. Second problem is perspective. So these are all, like for the discriminator, these are all fine as dogs. But are they really? So perspective is an issue. And if you are now thinking of cross-domain synthesis in medical imaging, where it's not MR versus CT, exactly 3D to 3D, these might kick in. These might make your problem a bit more difficult to train. And you have to do really special domain-specific things to make sure this kind of problem is not happening. And then again, global structures. Again, these are supposed to look dogs, and the discriminator is fine, they are dogs. But if you are doing reconstruction and you end up with a global structure like this, then it's not really nice to say that, okay, these are really the realistic looking. All right. So I have created a reading list for the review. If you are interested in medical image analysis, I will really suggest that please take a look at our review paper. At least you get all the, more or less all the citations of GAN papers that's been done till so far, and then you can go into the medical image analysis part. I talked about some of the engineering places which you can look into. A big list of GAN papers are there in GAN Zoo. There are these theory works that you can start with, and there are 2 excellent blog posts. So some of these contents are also taken from Sanjeev Arora and Ferenc Huzger's blog post. In summary, GANs are unsupervised generative models with an adversarial twist. When done correctly, these realistic images, realistic looking images of unprecedented quality are possible to do. However, proxy of training in medical imaging, when you are looking for proxy of training data or domain shift problems, GAN can be quite useful as a technology. There are issues of numerical instability and evaluation metric which you have to keep really in mind. So, in conclusion, the professors and group leaders, if you are planning to play with fire, I would suggest employ your best grad student to work on GANs. You might end up doing awesome things. All the best to those grad students who will be playing or actually are currently playing with GANs. You need it, because more often than not, GANs will backfire. When such explosions happen, the extinguisher might lie in looking at the real losses that the generator and the discriminator is giving. That's where you should probably start looking at to figuring out the problems are. But when they will finally fire, be ready for some fireworks. Thank you so much for your attention.